Welcome to a lesson with Dr. Powell. Let's take a look at taking the derivative of just a single variable function, but we're going to see how we can apply the techniques of the chain rule for multivariable derivatives in order to get at this derivative just a little bit better. What if we had something like this, the square root of like cosine of x all over sine of x raised to the x power. So something silly like this, okay? How would we go about doing this? Well, if we wanted to, we could think about this, maybe replace those x's with t's for now. Let's do that, replace them with t's. Okay, that was to the tth power. And let's kind of think about this in parts. Let's think about this as being a function x over y to the z. So kind of like a 3-variable function. See, f of x, y, z. Then let's think about a function x, y, z, or kind of like a vector function with 3 components, where we have x of t, y of t, and z of t, where they are, so let's let g of t be a vector function, where we output cosine t, sine t, and t. All right, so remember that the derivative of the composition, which is what we see right here, this is the composition of these two guys. Okay, so the derivative of that composition is nothing but the derivative of this times the derivative of that with things plugged in respectively at the given places. So let's do that. Let's first take the derivative of this. Now see how we have 3 inputs. So, and we have 1 output. So our matrix will have 3 columns and 1 row. Okay, so we take the derivative with respect to x, treating everything else as a constant. Well, then it's just really square root of x divided by a constant, which is, think about it like this if you want to. So we're just taking the derivative square root of x. Okay, so now if we take the derivative square root of x, that's like 1 over 2 root x, right? That's the derivative of square root of x because you have x to the 1/2, bring the 1/2 in front, and x to the negative 1/2 just becomes on the bottom. But that's multiplied by that constant right there, which we can put everything under the square root if we wanted to. So just extend the square root to yz. So we're successful at taking the derivative of this with respect to x. Next, we take the derivative with respect to y. Okay, so everything else is a constant. So let's just, so in that case, we could think of this as being so keep everything out, keep the square root of x up there, and then it's just the square root of y to the z right here, which we could think about it as being y to the z halves, to the negative z halves even, times square root of x. That's what we're looking at with everything else being a constant. So taking the derivative of that simply means, and maybe we'll just keep it simple this time. Let's just have, bring the exponent out front. We have y to the negative z over 2 because we're treating everything else as a constant, minus 1 times square root of x. So this is like fx, this is like fy. It is easier to take a partial derivative than it is to take a full derivative, but by doing it in parts, we can find the derivative very nicely. So then if we want to find fz, okay, we do the same kind of thing, okay, where z is the only variable here. Okay, so so in that case, let's just look and see what we have. Is this? Just think of what that would be like. So everything else is a constant. So then that would be like a square root of x and And again, okay, this is like y to the negative z halves again, okay. And taking a look at that, z is a variable, but everything else is constant. So we could even rewrite this as y to the negative 1/2 raised to the z squared of x. Now the derivative of this is just, so like, it's like the derivative of like 2 to the z. What's the derivative? It's 2 to the z times the natural log of 2. So really here I'd get that times the natural log of y to the negative 1/2, and then just multiply that by y to the negative 1/2 raised to the z power. Wow. Okay, it's just that. So I put that in. Now this looks pretty nasty. However, if you had a computer algebra system or you're doing this kind of computationally somewhere, you'd at least know what to put in and how to work with it easily. And so, but practicing by hand a little bit kind of gives us a sense of a few things. Well, one, it gives us appreciation, but two, it knows how to actually program it, how to work with it. If we didn't have this down at least a little bit, we wouldn't be able to effectively work with this. So we get, this is our derivative of this. And then the derivative of the next one's a lot easier, right? Okay. Yeah, and that was to the z. Oh, that's a z. Sorry, that's not a 7. I just rewrote it wrong. That's a z. Okay. Z power. Okay, that looks a lot better. Okay, so just rewriting it wrong. Okay, so that is, so that derivative, and then we just take that and we multiply by the derivative of g, which is negative sine t, cosine t, and then we have t. Oh no, the derivative of negative sine t and derivative of cosine t, then 1. Okay, derivative. Okay, so take a dot product of this and this, which I'm not going to do. But if you just plug in x is cosine, y is sine, and z is t, look, and take a dot product, that is the derivative. Hence, we got the derivative. Thanks for watching.